but I was led astray. The day you walked away, you were the clock that was ticking.
So what they give us here is evaluate the following integral, and they just say I for some reason. I equals 1 to infinity, again, and then we have dx over x times 2x plus 5. Okay, so first of all, we can rewrite this using the limit as r goes to infinity, and this is just a technical thing. You kind of have to do it this way, so yeah. And this is the same thing as 1 over x times 2x plus 5, and then the dx is here. So this form, especially on the bottom, that should remind you of a certain method of partial fractions. So that should trigger your memory into like thinking of this method whenever you have something times a parenthesis, something in parentheses, basically in the denominator. Okay, so this is the same thing as, oh wait, hold on, I almost forgot the all-important limit in front, right? Don't forget this, otherwise it's mathematically incorrect. So we have 1 to r, and remember partial fractions, that means we're going to have something over, okay, and both of these on the bottom, they're linear, right? They're not those irreducible quadratic denominators, I guess. So we have just a variable over each one, okay? So we're going to have something that looks like that. That's a 5 at the end here. 5. Okay. My 5s look kind of funny sometimes. Okay. Alright, so now we're just going to solve for a and b. So we do the numerator trick. Okay, and we get this equals whatever our original one was. So p of x was actually just 1. So p of x equals 1, which is the same thing as writing 0x plus 1, right? So then if we compare the coefficients, so we have 2ax plus 5a plus bx on this side, and then still the 0x plus 1. So 2a plus b has to equal 0, and 5a has to equal 1. So we can automatically get a equals 1 over 5, so that's good. And then b equals a negative 2a, which turns out to be a negative 2 over 5. Okay, I'm going to go on to the next slide. Alright, so we figured out this already at the top. So a equals 1 over 5, and b equals negative 2 over 5. Okay, so now we're just going to plug this back into the integral that we set up before. So we have our limit in front as r goes to infinity, and then 1 to r, and then we have a over x, which is 1 over 5x, and then we have a minus 2 over 5, 2x plus 5, and then dx. Okay, so now what I like to do is I'll just simplify this a little bit, make it look a bit nicer and less confusing. So I'm going to take out the 1 over 5 here, and that'll just be 1 over r, and then x dx. I'm going to split it up too. This is just the way I like to do it, because I like to see the organization better. 2x plus 5 dx. So the first one, that'll just turn into a 1 over 5 ln x. But the second one, we need u substitution. So u is 2x plus 5, du equals 2 dx, and then dx equals du over 2. Okay, so I'll just rewrite this. Limit as r goes to infinity of 1 over 5. I guess I'll write the ln x here. So this is ln, absolute value of x, and then minus 2 over 5, and we'll do the u sub here. So this is u to the negative 1, and then du over 2. Okay, and you see how the 2 inside, that's a 1/2, and it cancels with the 2 outside, so that's good. And we can integrate the rest of it now. So this is 1 over 5 ln absolute value of x, and then minus a 1 over 5 of ln u, which is now 2x plus 5. Okay? Alright, so now, and this is evaluated from 1 to r, right? Can't forget about the bounds. Okay, so then we have, let's see, we can do a little bit of ln work here. Or I don't know if your professor goes by ln or log. Sometimes they'll just go by log to represent the natural log. But anyway, so once you consolidate this, we get ln x over 2x plus 5. And then this is to the 1/5 power. Or, I mean, you could keep the 1/5 in front too. Let's just do that. So we'll just keep 1/5 in front to make it easier. Okay? Alright, and this is still from 1 to r. So on the next slide, I'll start evaluating it. So we're going to plug in r, and we actually get, let's see, we get a, well, we still have the limit in front because we haven't plugged in infinity for r. We're just plugging r into the, well, we integrated. Okay, so then we get 1 over 5, and then I guess we'll do ln of, well, we have r over 2r plus 5. And then this is, well, yeah, I guess we could do minus 1 over 5. And then ln, and we have 1 on the bottom, so it's going to be 2 times 1 plus 5, right? Okay, there's a lot of absolute values going on here. Okay, so this simplified is going to be 1 over 5, and I'm just going to bring that out, and we can divide these. Again, properties of ln's. So then, oh, this is an absolute value, sorry. R over 2r plus 5, and this was a 1 over 7, but now it's going to be a 7 over 1. Okay, I don't know why I put a parenthesis there, but anyways, so that's what it turns out to be. And then, let's see, when we actually plug in the infinity, let's see what we get. So we have a 1 over 5 out here, and then we have an ln of, and then there's a 7r on top, so 7 times infinity over a 2 times infinity, and then plus 5. Okay, so here's a quick thing about like plugging in infinity and stuff. Whenever you have infinity, it kind of dwarfs any constants around it. So this positive 5, in the long run, that's going to be basically 0. Okay, but then when you have coefficients, because it's multiplying times the whole infinity number itself, then we can think of infinity as a certain like large number. So these top and bottom, they're actually going to cancel. And our final answer will be 1 over 5 ln of 7 over 2. Okay? Alright, oh, well, and then that also, just if you want to know, is about 0.251. Okay? I told you my 5s are kind of funny. Alright, I'm just not going to go with the box because, okay, I'll write it down here. 0.251. Okay? So that's the answer to 42.